Alright, welcome back. So, we're continuing for a bunch of free response questions, this time dealing with related rates. So we're going to derive and integrate rates of change. I've got a swimming pool in the shape of a cylinder with a radius of 12 and a height of 4.
Mr. Brandon,
Yes.
are you recording?
Yes, I'm recording.
Oh, okay.
Okay. So radius of 12, height of 4. The pool has 1,000 cubic feet of water at a time t equals 0. During the time for the first 12 hours, water is pumped into the pool at a rate of pt cubic feet per hour. The table gives the values of pt. During the same interval, water is leaking out of the pool at a rate of RT, such that RT equals 25 e to the negative 0.05 t. I want to first use a midpoint Riemann sum with the subintervals of equal length, indicated by the table, to approximate the total number of water pumped into the pool during the first 12 hours. What do we need to do? Oh, 3 subintervals, that is.
So 4 times 46, or
Okay, you're right. So 4 by 46.
plus 6 times 57 plus 4 times 57 plus 4 times 62.
7 plus 4 by 62. Okay, so that's 3 rectangles that we have with their heights at the midpoint. Is equal to, it's roughly equal to, our integral from 0 to 12 of pt dt. Okay, so if we add all of this up, I've got this, I believe. Let's throw this on the other side. Integral from 0 to 12 of pt. If we add that, this is 20, 16, and I've got 660. Okay, do you guys match?
Yes.
Okay. What are my units for this?
Cubic feet.
Cubic feet.
Okay,
Cubic.
cubic.
Just cubic, or?
Cubic feet. Sounds good.
Okay.
So this is how much cubic feet of water was pumped into the pool during the first 12 hours. Okay, for part B, I want to figure out the total amount of water that was leaked out of the pool during the first 12 hours. So I'm going to jump over to Junho. What should we do?
The into 0 to 12. RT of DT.
Okay, perfect. The integral from 0 to 12 of RT dt, which is the same thing as the integral from 0 to 12 of 25 e to the negative 0.05 t. When I derive e to the u, I get e to the u times u prime. So when I derive, I multiply by u prime. When I integrate e to the u then, what should happen? When I derive e to the u, I get, write it like this. When I derive e to the u,
E raised to B minus E raised to A.
okay, I can do this without bounds actually. When I derive e to the u, I multiply by u prime. So when I integrate e to the u, I should do the opposite. How would I undo multiplying by u prime?
Pardon, what?
How would we undo multiplying by u prime? So when I derive, I multiply by u prime. So when I integrate, I should be able to undo this. How would I undo that?
Times U prime.
If I derive, I times u prime. So how would I
Uh,
undo that when I integrate?
Derive by U prime.
Divide by u prime. Every time we're integrating, we're just doing the opposite of whatever we did when we derive. So for instance, if we derive sine, I get cosine. If I'm working backwards when I integrate cosine, I get the sine. So I just did the opposite to work backwards. So if I want to work backwards, get from here to here, I would have to divide by u prime, right? So that's really what I'm doing here. Okay, so with that in mind, if I integrate from 0 to 12 of 25 e to the negative 0.05 t, my 25 is a constant, so I'm going to pull that out. So this will be 25 e to the negative 0.05 t divided by 0.05 from 0 to 12. And then we can
Okay.
plug in our upper bound minus lower bound. So if I'm dividing by 0.05, that's, I'm going to write this as a fraction, dividing by negative 5 over 100. If I'm dividing by a fraction, I can flip and multiply. So this will become 2500 over 5 for my fraction here. And it would be negative, because I have a positive and a negative. Times e to the, I've got 5 over 100, that's negative, times t, 12. Okay, minus negative 2500 over 5 times e to the 0 power, which would be 1. Okay, 2500 over 5 is how much?
I got 225.594.
For 2500 divided by 5?
No, for the whole equation.
Oh, okay. I'm gonna do step by step to double check, but I've got 2500 divided by 5 is gonna be how much?
5,000.
Okay, 500, so minus 500. I've got another minus 500 here times 1. So on this side, I'm going to be adding 500. And then over here, I've got e to the negative 5 times 12 is 60 over 100 is e to the negative 6 over 10, or negative 3/5. Okay. That's as far as I would go if I was doing this by hand. However, you're right. This is 225. 0.594. What are my units?
Cubic feet.
Yep, cubic feet again. Okay, double check really quick, but okay, this is with the calculator. So, we could just type in from this point. We'll double check while we're here. This is the integral from 0 to 12 of 25 e to the negative 0.05x. Is 225.594. Okay. And then I want to use these results to estimate the volume of water in the pool at 12 hours. Okay, what would we need to do? Okay, there's 3 things that we need to know. What 3 things do we need to know in order to know how much water total there is in the pool at 12 hours?
The height.
Um,
So that's 4 feet.
There's 1,000 cubic feet of water.
okay, how much water we started with?
1,000 cubic feet.
Okay, plus...
Oh, the plus the rate what is coming in minus the rate what is going out.
really close. Not the rate, but...
Oh, so the cubic feet
right, the cubic feet. So,
after
starting water plus
12 feet.
water,
After 12 hours.
water in minus water out. Okay, so I'm going to take this in words and we'll rewrite that as an equation. So, starting with Junho's. Junho, you're right, we've started with 1,000 cubic feet of water. Plus however much water we have in it t would be the integral from 0 to t of which one? How do I find out how much water we pumped into this?
P of T.
P of t dt? Okay, minus the water that we drained out would be the integral from 0 to t of what?
R of T dt.
T dt. Okay, so if I want to find this at 12, we would do the same thing. 1000 plus the integral from 0 to 12 of pt minus the integral from 0 to 12 of RT. And we actually already have those numbers, because in part A we found PT at 12, which was 660. And in part B we found RT at 12. The amount of water that we had drained out in those first 12 seconds was 225.594. Okay, so that's 1434.406. And then what are my units?
Cubic feet.
Okay, cubic feet again. So this is at t equals 12 hours. There are 1434.406 cubic feet of water in the tank. Any questions on what we did here?
No.
No.
Okay. Part D. I want to find the rate at which the volume of water is increasing at the time t equals 8 hours. Okay. And then once we know how fast the volume is increasing, I want to know how fast the water level is increasing. So first, how fast is the volume of water changing? What would my equation be?
The derivative of the equation before from the volume.
Okay, if we did that, the derivative of 1000 would be a constant, that's 0. The derivative of this integral would be my original rate, which is pt. And the derivative of this integral would be my original rate, which is RT. So this is just pt minus RT.
T minus.
Okay, here it is again. So if I derive the integral from 0 to t of pt dt in terms of time, I'll get pt times 1 minus p at 0 times 0. P at 0 will cancel. Pt times 1 is pt. We do the same for RT. Will give me a rate of pt minus RT, which makes sense. So my total rate of change in the amount of water would be how fast water comes in minus how fast water comes out. And how much water we had originally in the tank doesn't change how fast water is going in or out. Okay, so this is the change in my amount of water, which we actually marked as... Oh. Okay, I'm going to keep this as V prime because they actually gave us a volume here. Volume is V. So in that case, I'm going to mark all of these W's as V's instead, so I can match what they had. Okay, so I need to know I need to know this rate at t equals 8. So v prime at 8 equals p of 8 minus r of 8. What is p of 8?
(25e raised to the negative 0.05 times 8 power.
That's r of 8.
Oh,
Okay, what was p of 8?
60.
60. Perfect. So that's straight from the table. Okay. So we'll grab that really quick. (60 minus 25 e to the negative 5 over 100. Excuse me. Times 8.
bless you.
Thank you, you too. Is 43.242. And what are my units?
Bless you.
Thanks.
Cubic feet per hour.
Cubic feet per hour. This is the total rate of change of the water when you consider how fast it's coming in and how fast it's coming out. My net change is an increase of 43.242 feet per hour at exactly 8 hours after we started. Okay, then if I wanted to solve for how fast the water level is rising, what equation would I need to use?
The pi r squared
Perfect. Pi r squared h
times.
is the volume of
Yeah.
water that's in the tank right now. Therefore, when I derive this, since my radius does not change regardless of what the water level is, my only variable here is height. So when I derive this, v prime should equal what?
Uh, 12 pi r.
Okay, I'm doing that because this radius is always 12, no matter how high the water level is in the cylinder, right? The radius never changes, even if the water level changes. So if that radius is constant, then we don't have to treat it as a variable. So my volume is really 144 pi times h. If I derive that in terms of time, what will I get?
dh over dt.
dh over dt, perfect. Okay, and this v prime is dv over dt, if I want to do that to keep my units right. So this is dv over dt at 8, which is 43.242. So I could say 43.242 is equal to 144 pi times dh over dt, and use that to solve for dh over dt at the time t equals 8. If I do, 43.242 divided by 144 pi. Should give me my answer. So I'm going to take this whole thing and divide by 144 pi. Okay. Gives me 0.096. What are my units?
Cubic feet per hour.
Close. Really close.
Oh, feet per hour.
Feet per hour. So this is just measuring a change in height, not a change in volume. Okay, any questions on what we did for the last part?
No.
No.
Okay. So homework's going to be questions 1 and 2.
Okay.
And I will post this one up to the WeChat.